A very warm welcome to all of you for this session, which will feature the fourth keynote talk of the WINE 2017 conference. It's a pleasure for me to invite Professor Ariel Procaccia to deliver this keynote talk. The AGT community over the recent years has seen the rise of many stellar young researchers who have done very influential work. And certainly Ariel is a leader among that select group of stellar young researchers in the AGT community. He's currently an associate professor at the Carnegie Mellon University. He has done extremely intense and influential work in a wide variety of areas covering algorithmic game theory. He's worked in voting, he's worked in computational social choice, he's worked in computational mechanism design, and his influential work has been shown by at least half a dozen best paper awards that he has won, including a best paper award in EC 2014 and EC 2016. So he started off his glorious innings with the Victor Lesser Amas Distinguished PhD Dissertation Award way back in 2009, and he has not looked back from then. And in 2015, he got the Sloan Research Fellowship. In 2015 again, he got the very prestigious Computers and Thought Award from the International Joint Conference on Artificial Intelligence. And I'm sure we're going to see many more stellar contributions from Ariel. So with this, I will let's invite him with a wide applause and invite him to deliver the keynote talk in WINE 2017. Thank you.
Thank you so much for the kind introduction. Thanks for inviting me, and thank you all for coming today on the last day. It's great to see so many people still sticking around. So the topic of the talk is extreme democracy. And I want to start with a quote from Pia Mancini. She's an Argentinian kind of politician, a new kind of politician. She gave a very popular TED talk a couple of years ago. And in this talk, she quoted Marshall McLuhan, who was a Canadian professor, as saying that politics is solving today's problems with yesterday's tools. So you may be wondering why I'm not quoting Marshall McLuhan directly. The reason is that he didn't actually say this. He said something similar, but not about politics. Still, I like this version of the quote, so I'm quoting Pia Mancini with this version. And the point I want to make is kind of similar, which is that the world has really changed in the last decades with modern technology, but the way we do democracy hasn't really fundamentally changed for centuries. So it seems like really a good time to rethink how we do democracy. In particular, the theme of the talk is that computer science has a lot to contribute to this discussion. So I want to argue that we should be thinking both about how we do democracy, the practice of democracy, and also the ways in which democracy can be applied. So trying to increase the reach of democracy by thinking about new applications domain through, you could call it democratic thinking and computational thinking. So I'm going to illustrate this theme through three projects that we've worked on recently. One is in the space of liquid democracy, which is a paradigm that allows voters to delegate their votes, and these delegations are transitive. The second is going to be participatory budgeting, which is the idea that a city can allocate its budget by eliciting preferences from its residents and aggregating them to get a budget. The third part, I call it virtual democracy. It's a term that I came up with for the purposes of this talk. But the idea is that we'll make decisions by having a virtual election among machine learning models of real voters. And I'll show you how we want to use this approach in order to make ethical decisions in AI. I'm hoping that you'll leave the talk with the feeling that the whole is greater than the sum of its parts, in the sense that there are some really exciting processes happening now in the real world. Some of these things are really gaining steam right now. And there are very unique and interesting opportunities for computer science in general, and I think in particular for this community of economics and computation. So I'm going to start with liquid democracy. This is joint work with my student Anson Kang and my postdoc Simon McKenzie. I'll give you the full references at the end of the talk. Okay, so just to put this in context, let's talk about a few popular forms of government. The first that's been, very common over the, history is monarchy, which is kind of similar to dictatorship. And here the idea is that you have a king or queen or dictator, and there's some decision to be made. The only vote that counts, the only opinion that counts is the opinion of the king, and that's how decisions were typically made. On the other extreme, there's this idea of direct democracy. So this was famously practiced in ancient Greece. And the way that worked is all of the citizens would gather in the same place. Everybody would vote on the issue at hand, and then they would take typically a majority vote and reach a decision. So one caveat regarding this is that, of course, women and slaves couldn't be citizens, but it did offer relatively wide participation, so a lot of people could express an opinion. The main shortcoming of this approach in today's society is that you can't be expected to be informed on every issue that comes up. There are so many issues, things are so complex. So in most cases, we don't have time or just don't have the information or the expertise in order to express an informed opinion, which is why this approach doesn't scale. So what we do usually nowadays in democracies is what's called representative democracy. And the way this works is as voters, we elect our representatives. We vote for representatives. And when it's time to actually make a decision, our representatives are the ones that vote in parliament on our behalf. So this works reasonably well, but it has many shortcomings. One of them is that our representatives don't always vote the way we would want them to vote. So once they're elected, they often serve other interests that are not necessarily aligned with the voters' interests. So this is where liquid democracy comes in. You could say that it's a paradigm that lies between direct democracy and representative democracy. And the idea is that as a voter, I can either vote myself directly, or if I feel that I don't have the time, that I don't have the information, I can choose to delegate my vote to another voter. And like I said before, delegations are transitive in the sense that if A delegates to B and B delegates to C, C would be able to vote on behalf of both A and B. So in this example, the voters have made delegation decisions. So you can see these decisions as directed edges in this delegation graph. And when it's time to vote, so this was done before the actual voting, when it's actually time to vote on an issue, the voters who actually vote are the sinks of this graph, the ones that don't have outgoing edges, that didn't delegate their vote. And in this example, we'll have two voters who don't have any incoming edges, so no delegations. They vote on their own behalf. This one person here has one incoming edge, so he is voting on behalf of two people, himself and this other person. This guy here is a super voter with a total weight of 6. So basically everybody with a directed path to that super voter is delegating his vote either directly or transitively to this person. So when it's time to vote, he's voting on behalf of 6 people overall. So I think this is a pretty exciting paradigm, and it's really been gaining steam in the last few years. Through deployed liquid democracy systems. So the first that I know of that really got a lot of traction is the liquid feedback system. It's the system used by the German Pirate Party, which is a party that's been quite successful for a number of years in Germany. They won some seats on the European Parliament, in national elections, and they sort of made their deliberations through this liquid feedback system, which is based on liquid democracy. In the last few years, we're seeing a related idea, which is parties that are basically hacking the system by saying, we're going to run for parliament, but then our elected representatives are going to vote according to the wishes of the party members, and the decisions by the party members will be made by a liquid democracy-based system. Right? So they're saying, we're going to work within the political system, but we want to bring liquid democracy into it in this way. So one party like that is the Net Party in Argentina. Actually, Pia Mancini, that we saw before, is one of the founders. And another is the Flux Party in Australia. Their app is also called Flux. So unfortunately, both of these parties didn't win any seats in parliament, but the fact that they were doing this and did receive some support brought a lot of attention to the ideas of liquid democracy. So this is really an up-and-coming paradigm, and I expect that it will catch on even more in the near future. So it seems like a good time to be really thinking seriously about what's the right way to do liquid democracy, and that's what I want to present to you. We're going to do it through a rigorous model. It's a model introduced in the paper, and I'll show you the ideas behind the model. So the basic structure is an underlying directed graph G that represents some kind of social network, where the set of vertices is the voters, and we have an edge between I and J if voter I knows voter J, in the sense of I could potentially delegate to J. You can even think of it as knows of J, so they don't have to be personal friends. Now, there are going to be only two alternatives, correct and incorrect. Okay, so this is an important point. What we're thinking of is a setting where there is a ground truth. Right? There's two alternatives, but one is correct. To give you an example, think about the tax bill that's being discussed in the US right now. So, and take your favorite measure of economic success, maybe the national debt in 5 years. Right? So that's an objective measure. And whether the two options pass the bill or don't will have some effect on that measure, will have some measurable success. But of course, we don't know what the outcome is going to be. So when we vote, we only have like a noisy estimate of which option would be better. Okay, so this is one example of a widely studied setting, and that's the kind of setting I want you to keep in mind. Now, because we have two alternatives, of course, the only reasonable way to aggregate votes is by majority voting. And of course, if we have delegations, a voter with delegations would count as multiple voters. Okay, now each voter, I, has a competence level PI, which is his probability of voting correctly. So think of every voter who actually decides to vote. When it's time to vote, would flip an independent coin with bias PI. If it's heads, he votes correctly. If it's tails, he votes incorrectly. And finally, an important point is this definition of approval. So we say that I approves J if I knows J, it's an edge in the graph, and the gap between the competence of J and the competence of I is at least alpha for some parameter alpha of the model. Now, this is a very big assumption, right? Because this plays strongly in favor of liquid democracy, right? It says I'll only delegate to somebody else if that person is more likely to make a correct decision than I am. The reason why this is justified, I think, is that the main result I want to tell you about is negative. It's a negative result about liquid democracy. So it will hold despite the strong assumption. Okay, this only makes the negative result more powerful.
You're assuming that the PIs are public?
No, so I don't need to assume that voters actually know the PIs exactly, but they sort of can know if there's a gap that's large enough. Okay, so
They know whether
yeah,
I knows whether I approve J or not.
Exactly, right. So actually, right, so even we'll talk about these delegation mechanisms that see this approval relation and make decisions based on that. So the approvals are public knowledge, like I can know if there's a big enough gap, but I don't have to know what the exact PIs are, and I won't make use of that information. So multiple neighbors can be approved. Okay, so the way to think about the approval relationship is I could potentially delegate to J if I approve J. Okay? We'll see that I can choose, some of the neighbors to delegate to. I can even delegate to neighbors at random, according to some distribution.
Does I know who J approves of and so on, or does he only know his neighborhood?
Yeah, so we'll talk about that. It's a good question. Right, the question was, does I know who J approves of? We'll get to that. We'll talk about different type of delegations.
This probability you are telling that confidence level.
Yeah.
What can be the value? It will be 0.5, either correct or incorrect.
Uh-huh. So.
Can it be some other value?
Oh yeah, sure. So if a voter is very competent, it can be 0.9, or it can be any value between 0 and 1. Right? So 0.5 would say like I have no information, I just flip a coin. But it can be below 0.5. Maybe I have wrong information. Maybe my opinion is biased by some wrong views.
Do you have knowledge about their connected voters only, or about all the?
Yeah, we'll get to that. Okay, so that.
If they have idea about all the voters, then they can choose a path such that would go maximum.
Yeah, sure. So I guess a good way to think about it is they only know about their neighborhood, only about the edges, so they can only approve of neighbors that they know. You could say, well, I can expand the graph to include more vertices if there's some path, but the results will be independent of these kinds of concerns. Yeah.
So I was just curious, for example, we are implicitly assuming that there is a ground truthness which is called correct and incorrect, and for everybody this is the same correct, whatever decision you take is correct for me is correct for you as well.
Excellent.
So, I mean, those situations, in many times in democracy, is it the case?
That's a very good point. So the question was, why does everybody have the same metric in mind? And my answer to that will be the same justification that I gave to this point, which is, it's an assumption, but the negative result would hold despite this assumption. So this helps liquid democracy when everybody has the same objective in mind, and the negative result will hold despite this additional edge I'm giving to liquid democracy. Yeah, last question, and then we should move on.
Won't there be cycles in the graph?
Another very good question. So there could potentially be cycles. In the real world, under this assumption, we cannot have cycles because we only delegate to people who are strictly more competent than us.
But you said that it is I's rating of J. I and J might both think of each other as...
So the PIs and PI and PJ are sort of fixed. So they are the actual competence level. And we're saying I could only potentially delegate to J if J is strictly more competent. So here, this is one nice aspect of this assumption. We don't have to deal with cycles. In the real world, it's something we can maybe talk about later, but it's a tricky issue, like how to deal with cycles. Because definitely in liquid feedback, for example, delegation cycles happen. And it took us quite a bit of work to find out what they actually do to deal with cycles. Okay, so I want to show you an example of where liquid democracy can mess up in this kind of model. So think about this star example, where the arms have competence 0.6, the center has competence 0.8. Under direct democracy, and think about a lot of arms, not just 8. Under direct democracy, what we get is that the expected number of correct votes is close to 0.6 times the number of vertices. And we'll see a number of correct votes which is close to the expectation. So it's very likely that direct democracy, when everybody just votes directly, the majority will be correct. On the other hand, if you're saying, well, the center is significantly more competent, why not delegate to the center from the arms? But then the center is the only one who's making a decision. He's pretty competent, so with probability 0.8, he makes the right decision. But probability 0.2, which is significant, he would make the wrong decision. So by delegating to a more competent voter, we actually lose in terms of probability of making a correct decision. So what I want to think about is, can we avoid this phenomenon? Can we decide on delegations in a more clever way so that this kind of thing wouldn't happen? So in order to think about it, we define this idea of delegation mechanism, which just decides for each voter whether they delegate and to whom. And this delegation can be randomized. In particular, and this goes back to some of the questions by Nikhil and others, we're interested in this concept of local delegation mechanism, where the delegation decision is for voter I is only based on the neighborhood of I. And one justification for this is this sort of captures what happens in practice, where voters make their own delegation decisions based only on local information. So examples of this type of mechanisms is, delegate to a uniformly random approved neighbor, don't delegate with probability 1/2 and delegate to a specific approved neighbor with probability 1/2, or don't delegate at all. If nobody delegates at all, that's also a local mechanism. It just says, don't delegate with probability 1 for every vertex. Now, I want to formalize the kind of property that I just talked about, trying to avoid the example on the previous slide. So the way we formalize it is using this property called do no harm. And the idea is that we never lose significantly by doing liquid democracy instead of direct democracy. A bit more formally, for any epsilon, the loss, which is the difference in probability of getting the correct answer between liquid and direct, is at most epsilon on all sufficiently large instances. Okay, so that's how we formalize the idea of we don't want to lose. Now, this property can be achieved by not delegating at all, by direct democracy. So in order to basically avoid that kind of trivial solution, we are also interested in the positive gain property that informally just says that there are some examples in which you actually gain compared to direct democracy. And the negative result that I advertised before is this one, which says that no local mechanism can satisfy both of these properties. And this is true for any value of the parameter alpha, that decides when delegation can actually happen, when approval happens. So even if I only delegate when I have competence 0.001 and you have competence 0.999, we still have this negative result. So So the proof is kind of detailed, but I think the underlying idea is very simple. So I want to illustrate it to you in like 2-3 minutes. So the idea is if you have a local mechanism that has the positive gain property, there should be some neighborhood where delegation actually happens with some constant probability. Right? Otherwise, you won't be able to gain. So let's say this is that neighborhood. And what we're saying here is that the gray vertex has 3 approved neighbors, which are the solid edges, and 1 neighbor in the underlying graph, which is not approved. So this is the dashed edge, okay, just for example. And let's say the delegation happens with some probability between the gray vertex and its approved neighbors. So I'm going to set the PIs in a way that realizes this neighborhood. Okay? And now what I'll do is I'll replicate this neighborhood in a way that keeps the same blue vertices, but creates new green vertices. And I do it in a way that from the viewpoint of each one of the low competence green vertices, the neighborhood looks exactly the same. So under liquid democracy, all of these green guys will delegate with some constant probability to the blue vertices. Now, in addition, I'm going to add a bunch of other vertices whose PI is kind of a mess. It's very delicate, and you actually need to work a bit to prove that it can even be set correctly. But the way we do it fraction of correct green vertices or close to it in order for the majority to be correct. Okay, even if that fraction is small, it's enough to get a majority. On the other hand, if many of the green vertices delegate to blue vertices, there's a constant number of blue vertices, and with constant probability, all of them vote incorrectly. And when that happens, that shifts the majority in the wrong direction. So in this way, we create a constant gap in probability between liquid democracy and direct democracy, and we can make this example as large as we want by just replicating more and more green vertices. Okay, so that's the high-level idea. So what we saw in this construction is that the problem with local delegation mechanisms is that they can't identify situations where few vertices amass a large number of votes. An obvious way to circumvent this problem is to define this non-local mechanism, which we call greedy cap, that just says, we are allowing delegations, but we're going to cap the weight of any vertex at some cap C that may depend on the total number of vertices N. And what we can show is that under a truly mild assumption, if you set the cap correctly, this would satisfy the 2 properties. So here, our proof is very long. I'm sure there's an easier way to prove it, but I don't want to go into the proof because it's really detailed. I do want to speak a bit about the conceptual implications of this. One really cool thing is that there's been this discussion of an issue with liquid democracy where we have super voters who have too much power. So for example, this guy is a linguistics professor in Germany. And this article in Der Spiegel talks about how he amassed so many votes, he was so popular, that his word was basically law. When he made a decision, he would shift the majority, and that would determine the outcome. And people were obviously very unhappy about the situation, at least some people who are not this guy. So what greedy cap would do is prevent this kind of situation by limiting the weight of any voter. But what I really want to take you to take away from this part of the talk is not that the greedy cap is a great mechanism, because remember that we made very strong assumptions to help liquid democracy. I think the main point is that local mechanisms are inherently very limited. And the argument I hope you're convinced of is that centralized mechanisms could be the next step for effective liquid democracy systems. Where we give voters multiple delegation options, we see who they approve, and then we can centrally decide who delegates to whom. So this is the topic of some of our ongoing work, and I think an interesting direction for this line of work. Okay. So switching gears, let's talk about participatory budgeting, but let me first ask if there are any other questions about liquid democracy. Don't be discouraged by the fact that I cut questions before. We can go back to asking questions now. Yeah.
So with liquid democracy, would something like PageRank or eigenvector centrality automatically get you a greedy cap algorithm?
That's an interesting question. I don't think so, because if you, if you have the star, for example,
Well, I'll put one
so
more
the stationary
spin.
distribution would give the
Right, so
center.
I'll say one more thing. You cannot, every voter must have at least one outgoing edge,
Oh.
which PageRank kind of enforces by
Yeah.
doing 1 by n when it bootstraps. And now I'll re-ask the question.
Yeah, no, that's an interesting idea. So definitely, like I said, without this assumption, it wouldn't happen. With this assumption, possibly, it's definitely an interesting idea.
I have a question about like your latest result, like the one about the log n.
Yeah.
Should I interpret this as a positive or as a negative result? Because in a sense, I mean, if you can only amass so little power, then effectively you would need some mechanism that's like very similar to our current elections, right?
So you're saying it's a disadvantage that the weight is so limited, it's only like square root of log?
Yes.
Yeah, I agree. I think it's a good point, right? So the point was, are we really limiting the mechanism by setting the cap so low? One point here is that it's not obvious that this is like the highest cap one can give, right? So that's what we need for our analysis, which, like I said, there must be a simpler analysis than what we did. So it could be the case this would work with a higher cap. But again, just let me reiterate that I don't view greedy cap as a great mechanism, right? So I think you're right that it's not necessarily the mechanism we would want to use. It just emphasizes the point that, makes the mathematical point that non-local mechanisms don't suffer from the same shortcoming that we saw for local.
So in direct democracy, you're assuming each coin toss is independent,
Yes.
right? So how much of this is a result of that? Because it seems to me what's happening here is you're trading off concentration for kind of correlation.
Yeah, I think it's a good point. Right.
And in real world, it's not really independent. So in direct democracy, you're not going to get that concentration that your analysis gives you.
Right.
So.
Right, I think it's a good point. I mean, and there's definitely been quite a bit of work in the voting space as well about correlated votes. I think this will actually be the last question because we should move on. So there's definitely there's work in voting about correlated votes, including some work that we did. I guess my answer to you will be the same answer as before, which is, if you make you could make the model more complex by saying I'm allowing some correlations. You could, so potentially if you impose some structure in the correlation, you could avoid this. But I would say in a more general model, a special case of it would be independent votes, and then the negative result kicks in. Right? So it's maybe possible that by imposing some correlation structure, you could avoid this negative result, but that would be a pretty specific assumption to make. I actually want to move on, so let's save other questions about this to the end of the talk.
Can I ask my question now?
Let's save it for the end, okay, if we have time. Okay, so let's move on to participatory budgeting. This is work with Herdis Benades, Raprava Nath, who's somewhere in the room, and Nisarg Shah. So here, it's again a paradigm that has really gained steam in recent years. Like I said before, the idea here is that we want, cities want to get their residents to participate in the process of allocating the budget. The origins of this is in Porto Alegre in 1989, a city in Brazil. And they've actually really flourished under the system. They've been allocating their entire budget using a participatory budgeting system. And according to many metrics, there's a lot of work in political science about this. They've really flourished under the system. In recent years, it's been really catching on. So in some of the major cities of the world, they're not allocating their entire budget, but significant sums according to participatory budgeting. So Paris, I think, is the world champion outside of Brazil. Last year, they had a €100 million participatory budgeting election. Madrid had a €24 million election. And New York, here it's a guesstimate because I had to get information from different wards, but my guesstimate is $31 million. So these are very large sums, and I think they're only, you see a very obvious trend of increasing from year to year. So it's getting bigger and bigger, and it's already a very big phenomenon. So let's again think about, how we want to do participatory budgeting in a rigorous model. We're going to have a set N of voters that are voting over a set A of M alternatives, and the total budget is capital B. Every alternative A has a cost C sub A, and every voter I has a utility UI of A for alternative A, so far simple enough. Now, for every subset of alternatives X, the total cost of X is, of course, the sum of costs of the individual projects. I'm going to make a strong assumption that the utility of I for a subset X is also additive. It's the sum of individual utilities. I think this assumption is justified because if you look at participatory budgeting elections, the projects or the alternatives are generally independent. So additivity is usually a strong assumption. I think here it's well justified. Now the goal is to find a subset of alternatives X that maximizes the utilitarian social welfare, the overall utility of all of the voters for the subset. So I'll denote it in this way. Subject to the budget constraints that the total cost is at most the budget. So here I'm adopting the formalism of Goel et al., work by Ashish Goel and his team from Stanford. They've done really fascinating work both on the theoretical foundations of participatory budgeting, but also on the practical side, they've administered quite a few participatory budgeting elections in the US. And we'll come back to some of their ideas in a minute. Now, if you look at this last bullet, you must be thinking, this is just a knapsack problem, because every alternative, its value is going to be the social welfare for that alternative. We have the budget constraints, we have a cost for every alternative, and we just want to maximize total value subject to the budget constraint. The problem is that we can't go around asking voters for their utility for each alternative. That wouldn't be really practical, asking people for all of these numbers. In some of these real elections, you have at least 50 projects in the final stage. So what happens in practice instead is that votes are elicited that try to capture the preferences through a different format. We're going to refer to this format as an input format. So I want to show you a couple of input formats that people have been discussing. And I'll do it through this imaginary city and 4 projects. And I want to show you the imaginary cost of every project and the utility to a particular voter. So I'm going to take the viewpoint of one voter and show you how he translates his utilities into votes in different formats. So here are the alternatives. We have a town square with utility 8 and cost 9, a bike lane with utility 2 and cost 1, there's a park, and we can invest in clean energy. Now the first input format is very natural from a social choice viewpoint. It's just ranking by value. So the voter would sort the projects by utility and then submit a ranking that's consistent with this sorted order. So here, it would put the town square first, then clean energy, then the park, and then the bike lane. An idea proposed by Goel et al. Is let's, instead of just looking at value, let's let the voters think about cost as well, and get them to sort the projects by bang per buck, or value for money. So here we would sort by the ratio of utility and cost. And in this example, this would actually give the reverse ranking. So we would have the bike lane, then the park, then clean energy, and then the town square. Now, the input format that Goel et al. Really advocates strongly is knapsack voting. And this has actually been independently used in Europe for the last couple of years. For example, the Madrid election that I mentioned, 24 million euro, used this input format. So the idea is that we ask every voter for their optimal set subject to the budget constraints. Essentially, we ask every voter to solve their personal knapsack problem. So if, for example, the budget is 9, our voter would choose clean energy, the park, and the bike lane. The total cost is exactly 9, and the total utility would be 11. That's the optimal, like the voter's personal optimal solution. Now, the fourth input format is something we introduced in our paper. We call it threshold approval. And the idea is that we set a threshold, and we tell voters, please approve the alternatives whose utility is above the threshold. So for example, if we set a threshold of 5, our imaginary voter would approve the town square and clean energy and would not approve the other alternatives. So these are all reasonable input formats. And the question is, which one should we use? The main conceptual contribution in the paper is giving a rigorous framework in which we can answer this question and objectively compare different input formats. So the framework relies on this idea of implicit utilitarian voting that Brandon introduced really nicely in a great talk yesterday. I'm going to formulate it a bit differently because it's a slightly different setting. So the idea is that every voter I reports a vote sigma I that is consistent with his utility function in the same way that we saw in the previous slide. You can translate your utility into a vote in each one of the formats. So sigma I will be specific to a given input format. And we're interested in voting rules that take an input profile as the input, a vote from each voter, and maps it to a budget feasible subset of alternatives, possibly at random. So it could give us a distribution over budget feasible subsets. Now the main definition here is this definition of distortion, which comes from a paper of mine with my PhD advisor, Jeff Rosenshine, from 2006. What this is trying to capture is the idea that we want to maximize utilitarian social welfare, but the voting rule doesn't actually have access to the utilities. It only has access to the observed votes. So distortion tries to capture how much the voting rule is losing because it lacks this information that it needs to find the optimal solution. So specifically, the distortion of a voting rule F on an input profile sigma is the following expression. We look at the ratio between the budget feasible welfare maximizing subset of alternatives and the expected social welfare from the subset chosen by a randomized rule F. Okay, so this is how much F is losing. But we're doing it in the worst case over all possible utility functions, utility profiles that are consistent with the observed votes. So we're basically asking how bad things can be for a particular choice by the voting rule based only on the observed votes. Now the nice thing about this concept is that it allows us to think about how good or bad an input format is by associating with an input format the worst case distortion of the best voting rule. So the way to think about this is, given an input format, I'm going to choose this F in a way that would optimize this expression. And then I will look at the worst case over all possible input profiles. Remember that this is specific to one input profile. I want to ask how bad can things be across all possible input profiles. What this is trying to capture is inherently how useful the information encoded in the votes is for maximizing utilitarian social welfare in the worst case. So the theoretical results in the paper focus on answering this question, bounding this distortion. And here are the results. So the candidates are ranking by value for money, knapsack votes, and approval voting. So ranking by value has distortion order of square root of m up to logarithmic factors, where m is the number of alternatives. And similarly for ranking by value for money. Now knapsack votes is doing much worse. Its distortion is theta of m. And notice that this is horrible because if you choose a single alternative uniformly at random, that will give you distortion at most m. Right? So, I'm thinking about the case of a budget equals 1. So let's say choose a feasible subset uniformly at random, that would give you distortion at most m. But in any case, this is a really horrible result. And basically says that knapsack voting in the worst case contains no useful information for optimizing social welfare. Right? So this is really bad. The good news is that threshold approval does really great in terms of this measure. So its distortion is O of log squared of m, which is much, much better than the others. In fact, there's a forthcoming paper by Umang Bhaskar and Varsha Dani, Umang must be here somewhere as well, where they show that if you make some additional mild assumptions, the distortion under threshold approval can actually go to 1 as the number of voters increases. Okay, so this is sort of doing much, much better in this measure compared to these other input formats. Now then, the nice thing is that these theoretical results also have really nice implications in experiments. Okay, they do a good job of predicting what would happen in the average case. So these are some empirical results that we have in the paper. The data here was generously given to us by Goel and his group. It's from elections that they administered in Boston in 2015 and 16. And what we did was that we took the actual data, so it's 10 alternatives per election, between 2,000 and 4,000 voters. We took the actual costs of the projects or the alternatives, and to generate utility functions, we took the votes and we drew utilities uniformly at random that are consistent with the observed votes. And then once we have the utilities, we can derive from them votes in the different input formats and aggregate them in any way that we want. And what we care about is how well we're doing compared to the optimal solution for the utility profiles that we generated. Right? So for specific utility profiles that we drew at random. So this is an average case result. And this ratio, we're referring to it as the average welfare ratio. One thing to note is that all of these ratios are pretty close to 1. Right? So in the average case, things are doing much better than in the worst case, as often happens. What I want you to pay attention is two things. One is if you look at the 4 first input formats and aggregation methods here, these are the optimal deterministic aggregation methods for distortion, coupled with the 4 input formats that we talked about. But these are worst case aggregation methods. And what you can see is that their performance is ordered in the same way as we saw in the theoretical results for the worst case. Okay, in particular, threshold approval has the best performance. Another interesting thing here is this thing, greedy knapsack. So this is what's used in practice, for example, in the Madrid election that I mentioned. What they do is they take knapsack votes, and then they just sort the projects by the number of votes that it got, the number of subsets in which it appeared. And they just stick them into the budget greedily as long as they can. So if you can't put a project, you go to the next one until you run out of budget. And you can see that if you take knapsack votes with this greedy aggregation, things are pretty bad compared to some of these worst case optimal methods. So the take-home message here is that, from my biased viewpoint, threshold approval coupled with optimal distortion-based aggregation stands out as a promising approach to participatory budgeting. Nevertheless, the jury is very much still out. So one major challenge in the space is how to elicit these kind of votes effectively. What do we tell voters in order to get them to report whether their utility is above a threshold? How do you specify this kind of request? So this is actually the subject of ongoing work with collaborators from Ben-Gurion University in Israel, where we're running human subject experiments to try to answer this type of question. Okay, so that's it about participatory budgeting. Any questions about this at this stage?
Threshold voting, how are we setting the threshold?
Excellent question. So the threshold has to be set at random for the worst case results to hold. Right? If you force a deterministic threshold, you won't be able to get distortion better than square root of m, so you can do better than things like rankings. I can maybe try to give you a taste of what, the kind of voting rule that gives you the worst case distortion bounds. The way it looks like is it basically chooses a threshold uniformly at random from log m options, where we basically start from 1 over m squared and every time double the threshold. Right? So we have 2 log m options. There's a lot of other stuff that's going on. So we have, we need to divide the alternatives by costs. And essentially, we sort of guess a cost that would give us a lot of benefit. We guess a threshold. And we look at approval votes for alternatives of that cost that are above that threshold on a very high level. But I guess the short answer is the threshold for the worst case results has to be chosen at random. I'll say another thing, that for the empirical results, if you think about it a bit, when you have a distribution over instances, like in this average case setting, the optimal rule would actually be deterministic, right? Because we're dealing with a distribution on instances. We actually choose a deterministic threshold for the implementation from which we derive the empirical results. So the picture is kind of different between the theoretical results and the empirical results. Nicole?
For the distortion metric, when you're looking at your threshold value thing, you don't have to look at every utility function consistent with the ordinal ranking because you know something about the utility function based on the threshold. So I'm wondering if your approximation could be improved if you use that, like if you restrict yourself to that subset of utility profiles that respect the threshold that you've.
I mean, that's exactly what we're doing. So when we do the worst case optimal aggregation method, we're only, like the way the aggregation method works. Oh, you mean like for the theoretical analysis? Yeah. So we have matching lower bounds, right? So you wouldn't be able to do better. For threshold approval, okay, let me be a bit more accurate. For threshold approval, the lower bound is log m over log m. So, and the upper bound is log squared m. I don't think it's like a crucial gap, but potentially you could do better by changing the segregation method I told you about. But, in particular, if you think about the other input formats like rankings by value or value for money, then there the bounds are tied up to a logarithmic factor. So it's like a lower bound of square root of m, upper bound of square root of m log squared m. So you could, the aggregation methods also have a similar structure to what I described. You could potentially change it, but in the worst case, you won't be able to do much better. For the optimal aggregation methods we use in the empirical results, we actually explicitly compute the polytope of feasible utility profiles, and we optimize over that polytope. So when you do things in practice, you actually take that into account. It's going to be very difficult to analyze in theory, though. Okay.
The threshold routine, you are allowed only one threshold or multiple thresholds?
Yeah, so the result holds, the theoretical bound holds even when you only allow one threshold. For the Busker and the knee result that I mentioned to hold, you actually need to set a personalized threshold for every voter. But for our result, it holds even with a single. Right, okay, so that's a good point. The question was, what happens if we allow 2 thresholds? So in general, what if you allow 1 million thresholds, right? The more thresholds, the more thresholds you allow, the more accurate of an estimation of the utilities you get. In particular, you should get a smooth, convergence to a distortion of 1 as you add more thresholds. Of course, this adds to the cognitive burden of eliciting these votes. So I feel like 1 threshold sort of hits a sweet spot between how informative it is and the cognitive burden imposed.
Good to understand how it's smooth.
Yeah, I think it's an interesting question. We're actually looking at a similar question right now in joint work with Nisarg Shah and a couple of other people, which is basically, forget about the thresholds. If I just allow you to encode your vote, your utility in the best possible way, how low can the distortion be, depending on how many bits I allow you to encode your vote in. So that's a more, I guess a more precise version of this question of, I restrict you to thresholds, how many thresholds can you use? One more question, yeah.
So in real instantiations of kind of eliciting utility, 2 related questions. What's been your experience in terms of actually being able to figure out the real utility of a project? First question. Second is, the utilities could be along multiple dimensions. So multi-objective utility functions as such. Will that fit in the paradigm automatically or how would that?
Okay, so for the first question, the answer is I don't know. I mean, the question was about, eliciting. Okay, I know partially. So in this context, that's exactly the kind of thing we're checking in ongoing human subject experiments where we don't have results yet. The system is ready, but not the results. So I'll have an answer for you in a couple of weeks, hopefully. I do have experience with this in a different context, which is fair division. So we have a website called Splitit, which implements some fair division algorithms. One of them is dividing indivisible goods. And there we actually do ask people for exact utilities. The way it works is you have a pool of 1,000 points, and you have sliders, and you basically divide your points between different alternatives. There's also an assumption of additivity, which is an even stronger assumption there. But anecdotally, this seems to work well. I mean, the website has had quite a few users, and this seems to be working well, but we haven't done any rigorous scientific study regarding how well does this work compared to other alternatives. So those are the kind of questions we're trying to check right now in this context in the ongoing work. Remind me what the second question was? Multi-objective. Oh, multi-objective. So I would say, I mean, one way to maybe punt the question would be to say, okay, just take some weighted combination of all of your utilities and sort of summarize them as one utility. That would be a way of capturing that kind of setting and reducing it to this setting. Yeah, but I don't have a good answer if you really have different utilities on different dimensions. Okay, good. So let's talk about the last part, which is virtual democracy. This is joint work with my student Ritesh Nutigatu, my colleague in the machine learning department at CMU, Pradeep Ravikumar, and a bunch of collaborators in the MIT Media Lab led by Iyad Rachwan. So the starting point is this really cool website called Moral Machine, created by our MIT collaborators. What it tries to do is understand a modern incarnation of a classic problem called the trolley problem. So the situation is you have an autonomous vehicle that gets into an inevitable accident, like it has a brake failure, and people are going to die, so that's the grim reality, and the vehicle has to choose which people to kill and which people to save. So what the website does is it asks people to make this type of judgments, showing them 2 groups of people, 2 situations, and asking who will you kill, who will you save. So this is an example dilemma. So what you can see here on the left is the car would go straight and would kill 1 overweight man, 1 male doctor, and 1 baby. Or the car could swerve, right? So take an action and actually swerve, and then 5 people would die, and you can get the information about each one of the people. So what would you do? Most people in this situation would choose to kill the pedestrians and save the passengers simply because there are 5 passengers and 3 pedestrians. So by the way, one nice anecdote about this, which I noticed after the fact, is that if you look at the driver's seat of this car, according to any reasonable country, there's a baby in the driver's seat, right? Which kind of makes sense because you think like it's an autonomous vehicle, so you could have a baby there. But by the same logic, this must be an autonomous stroller because nobody is pushing it. And if you thought this example is wacky, so here you have a daring escape from the animal shelter with 5 animals in the car. And then you have to choose between the animals and the people. And here most human judges would, of course, choose to save the people. Right? That's a pretty natural choice. So what? Yeah. That's a good question. I mean, it's not one of the features, but that may be worth adding to the website. So what Iyad and his team hope to get with this website is some understanding of which features people care about. Right? How do people make these decisions, for example, in a way that depends on the culture they come from. And they've been incredibly successful at gathering data. So they've collected over 18 million pairwise comparisons from over 1.3 million voters. And the starting point of our project was the realization that we can use this large treasure trove of data to actually automate this type of decisions. So this is the approach that we proposed. The first step is data collection. So the idea is that we would ask people for pairwise comparisons about, on the type of dilemmas that we care about. The second step is learning. So here the idea is that we would learn a model of each person's preferences based on these pairwise comparisons that would allow us to predict what a person would prefer on dilemmas that we haven't seen. The third is summarization. So the idea is that we're going to need to make decisions very fast. And we can't really go and look at every individual model if we have millions of models. So the idea is that we would summarize all of these models as one big model of societal preferences that we can act on very fast. And finally, at runtime, we have aggregation. So the idea here is that we're facing a specific subset of alternatives, and we want to apply a voting rule to our model of societal preferences in order to make a socially desirable decision. The decision that society would want to choose if we went to all of these voters and asked them, what do you want to do on this dilemma, and aggregated their votes. So what I want to show you is a specific instantiation of this approach that we implemented and led to a system that we built that can make this type of decisions, I think, in a credible way. For the first step, data collection, this has already been done by our MIT collaborators. We have this large data set that I just mentioned. For learning, what we do is, this is basically off the shelf. There's no novelty here. So we use a model called the Thurston-Musteller model, or the Thurston Model 5. The way it works is that, if you take the viewpoint of one voter, the question is how would they generate a ranking over the alternatives or pairwise comparisons? So the idea is that every voter has a mean utility for each alternative. We have red, blue, and orange. And then what I'll do is I'll draw a sample from a normal distribution around each one of these mean utilities. So I might draw a red sample, a blue sample, and an orange sample. And then I order the samples in this order. So I would put blue first, orange second, and red third, even though the orange mean is above the blue mean. It's just a random sample. Now, in our instantiation, we take a very simple representation of the means using this linear representation. So the idea is that every alternative xi is a vector of features. On Moral Machine, there are 23 features. So things like, are they pedestrians or passengers? If pedestrians, are they crossing on a red light or green light? Omission versus commission, is the car going straight or actually taking an action and swerving? The types of people and so on. So 23 different features. The voter is associated with a vector of beta of parameters. And to get the expected, the mean utility, we take the dot product of the beta vector and the feature vector. A nice thing about this representation is that learning the maximum likelihood beta vector is a convex program, so we can do it very efficiently even on 1.3 million people. Okay, so for step 3, at the end of step 2, we've learned this 1.3 million models represented by vectors of parameters. And now we do a very naive thing. So we want to represent the entire society as a single Thurston-Musteller model. right, with some beta vector. So what we do is we just take the average of all of the beta vectors. So we have some theory to justify this, but I think really the main justification is the empirical results that I'll show you in a few slides. This thing works really well, even though it's a very naive approach. Now, where the technical novelty is in the paper is the last step, aggregation. So the situation is, after step 3, we have a single Thurston-Musteller model. And now at runtime, we're facing a particular set of alternatives. This Thurston-Musteller model induces what's called an anonymous preference profile, which you can think of as our predicted probability that a random voter would have any possible ranking, or like the fraction of voters that would be associated with any particular ranking over these alternatives. Now, this is a type of input that you can directly feed into a voting rule. But then there are a couple of challenges. One is which voting rule to use, which is the most ethical. And the second is how to do this very fast at runtime, because you don't actually want to unpack this Thurston-Musteller model and get like this explicit distribution over rankings. So we work quite a bit to answer these questions. We answer them in a general way in the paper. I'll just give you the special case of the theorem that we prove. So what we show is that if you have any voting rules satisfying some minimum properties, maybe not minimum, but pretty basic, monotonicity and neutrality, it would select an alternative that maximizes the dot product of the average beta vector and the feature vector. So very, very simple, although showing this is not trivial. And notice that this answers both of our questions, right? Because many of the voting rules you would care about agree on the same outcome. And computing this outcome when you have this average beta vector is very easy. Okay, so this is good news. I don't want to get into the theory. I just want to show you in 1 minute some of the empirical results. And maybe in the interest of time, let me actually skip to this second graph, which I think is more interesting. So this graph on the right looks at the accuracy of step 3 that I told you is this very naive summarization step. And what we did was, on the moral machine data, we have the 1.3 million models that we learned, and we look at two worlds. So one is we take these 1.3 million models, we apply a common voting rule called Borda count, and we look at the outcome for random subsets of alternatives that we might encounter. And then we do the same thing for the summarized models. So we take our models, we average them, we take the average beta vector, and we apply Borda count to this summarized model. And we want to see what's the probability that these two things would agree on the outcome, on the winner of the election. What we vary here is the number of alternatives per instance. So notice that on the right, if you have 10 alternatives, right, over here, 10 alternatives, the baseline would be 0.1, because if you chose at random, you would get that probability. And even there, we're getting 95.1% accuracy. Right, so this, this is, I think, to me, was a huge surprise that this works so well, despite being a very naive aggregation method. And one of the reasons it works so well is because we have so many voters. So we also have some experiments about how does this change as you increase the number of voters. With 1.3 billion, this is a very effective approach. Okay, so to just wrap up, let me mention, hopefully you've felt this. I'm really excited about this approach. I think one reason is that it applies not only to autonomous vehicles, but to many other domains. So to give you one example, there's a forthcoming AAA 18 paper by Freeman et al. Two of the authors on this paper you may know are Vincent Konitzer and John Dickerson. And they they independently came up with a related but distinct approach and applied it to kidney exchange. So the question they want to ask there is, we are matching donors and patients, and we want to break ties among matchings of equal cardinality based on societal preferences about which patients should we prioritize. So that's what they do. We have an ongoing project that I'm super excited about. It's a collaboration with a colleague of mine, Min Kyung Lee, who has been working with a food bank in Pittsburgh called 412 Food Rescue. And what we're doing is we're building on this approach to build an algorithm that would automate their decisions of allocating donated food items to recipients, which are usually food pantries and other nonprofits. So this is sort of work in progress. But really, I think the same approach can be applied in any domain where you have AI and ethical decisions come up. So the take-home message of this part is that we've built an implemented system that I think serves as a proof of concept. I wouldn't recommend deploying it right now, but it's a proof of concept that it's possible to automatically make credible ethical decisions without a formal specification of ground truth ethical principles. And I'm emphasizing this last point because I think this has been the main barrier to ethical decision making in AI. The fact that ethicists haven't specified for us, these ground truth ethical principles that we can encode in an algorithm. So this completely circumvents that by just saying, we trust democracy, hopefully, and to some degree, when we have many people and we make these democratic decisions, we can view them as credible ethical decisions on ethical dilemmas. So this is really, a fundamentally new type of application for democratic thinking in this kind of domain. Okay, so last slide, just to give you the bibliography as I promised. Strangely enough, all of the papers I talked about appeared in AAAI. So the first is work with Anson Kang and Simon McKenzie that will appear in AAAI 18. The second is work with Gerdes Benades for Pravanath and Sarg Shah that appeared in AAAI 17. And the ethical decision-making part is work with Ritesh Nitigatu, Neil Gaikwad, Edmund Awad, Sohan D'Souza, Yadil Juan, and Pradeep Ravikumar, which will appear in AAAI 18. Thank you so much.
We have time for a couple of questions. 3.
Brendan?
So at a high level, I guess you're circumventing some of these problems of not having a ground truth ethic by saying, I'll assume some sort of an equivalency between this like democratic outcome or something and the sort of true ethical state, right, in whatever sense. I'm curious how you would account for some of these like classic problems of the tyranny of the majority. So if it's the case, say in the US, that there's like a racial bias and 70% of people make this decision based on the race of the person, but maybe we actually think that's not the ground truth.
Yeah, I think that's a very good point. So, this approach suffers for any shortcoming of democracy. Right? The tyranny of the majority is not only a problem with ethical decision-making, it's a problem with any kind of application of democracy. Nevertheless, we still use democracy to make decisions, right? So, I mean, that's my viewpoint, that in general, I'm a big believer in democracy. It has its flaws, but, on average, it works reasonably well. And it just gives a practical approach to making these decisions. This is the first practical approach. We have no other way of making these decisions. So it's not a perfect approach. It's, it has some flaws. Tyranny of the majority would be one. But it's a way of making decisions right now that are credible. One thing I would add is, if you did come up with legal constraints or ethical principles, you could always add them on top of the system. Right, so the way we're thinking about this, and we explicitly say this in the paper, is, okay, if you came up with anything else that can sometimes make decisions, put it on top of that, try to apply these rules, and if you fail, then apply this approach. But this is something we can apply right now and is credible as far as democracy is credible.
So a related question, what is the intuition behind such a high accuracy? Some of the features that you mentioned, for example, 5 versus 3, almost everybody will agree. Animal versus humans, everybody will agree. So the confusion class, or like the features where people will disagree, like a doctor, one versus another. Can you give some intuitions in terms of what's the variance in the underlying signals?
Yeah, that's a very good point. Actually, I haven't thought about it, but I think I think you're absolutely right. That we looked a bit at like what the better parameters are in some of the decisions the system makes. So definitely the most important thing is what's called the character count, like how many people you have. That has relatively high weight. Then there are other interesting things. So for example, I think the threshold, like if I asked you to choose, or I asked a random person, or I asked the system, sorry, to choose between killing 10 men or 9 women, it would choose to kill 10 men. So it's not only, it gives a higher weight to women than men, but really the first order decision is the number of people. And I think you're right that, the way we're generating alternatives is by randomly drawing values for these features. So you would get a difference in terms of how many characters there are, and that could be one reason for this high accuracy. I think in practice, you would also have a difference in the number of characters. So this doesn't necessarily conflict what you would get in practice, but it is a good explanation, or it is the partial explanation. Very interesting point.
This will be the last question.
Okay, my question is about liquid democracy from before. It's about 2 of your assumptions that I think are possibly too restrictive, and I wonder if you're going to change them or remove them. So the first one is about having a correct or incorrect answer. How can you have that in a domain where there's people of right political leaning, left political leaning, they might want different things. And then having a global competency level relates to that point as well. Why would I want to delegate to a capitalist if I'm a big socialist or something like that?
Yeah, so I think both of these questions came up in some form, and I'll give my generic answer, which is, these are big restrictions. They work in favor of liquid democracy. For example, for the first point, everybody agrees on what the metric is. When everybody agrees and delegates according to that, that helps liquid democracy, and nevertheless, we get a negative result. Right? So it's, and the same thing goes for the second point, like we sort of are consistent in terms of how we delegate. All of this helps liquid democracy, and therefore makes the negative result more powerful. Now, I think one point we could address is, would the positive result still hold if you relax these assumptions? I would say at least for the competence thing, so even if you allowed in some cases, we haven't done this formally, but I discussed this with my colleagues, my co-authors, and we believe the proof can be adapted even if you relax that assumption. So if usually people delegate to more competent people, but sometimes they delegate to less competent people, the positive results should still go through. That said, like I said, I don't view the positive result as saying something very practical other than that non-local mechanisms don't suffer from the same shortcoming as local mechanisms. So it's not necessarily something that you would want to go, I wouldn't necessarily recommend trying to remove assumptions and extending that result, because I don't think that's the take-home message of this work.
So in the interest of time, we'll take the rest of the questions offline. And let's thank Ariel for an extremely interesting lecture on extreme democracy. A little gift for you.
Thank you so much.